And there are two steps. The first step is we're going to look at something called polar coordinates. This is like 7-point something in the book. I didn't look it up. The idea is we've been using coordinates that are x, y. We have a coordinate plane, we have an x-axis and a y-axis. We have an origin, which is at 0, 0. And, you know, pick any particular point, let's say 1, 3. Well, we know we go over 1, we go up 3. And that's our point. And that's a way of describing this point. An alternative method is using what we call polar coordinates, where instead of x and y, we have coordinates r and theta. R being just a distance, a radius, and theta being an angle. So a polar grid might look like this. I'm just kind of drawing in different angles here. We still kind of have an x and a y axis that we're not going to pay attention to. And let's say we have some point 4 pi over 4. Well, probably best to first look at the angle. Pi over 4, that's 45 degrees, or and halfway between here. You can think of this as a ray going out from the origin. And then we have a distance of 4. So 1, 2, 3, 4. And that's our point. Well, there's an equivalent point here too we'll get to. We could have x and y coordinates for it, but it's just another way of naming the point. Now, there's a lot of really cool stuff we can do with polar coordinates. I want to point you to your calculator if you have one, and you'll notice if you hit mode, down, let's see, 1, 2, 3, they have an option that is func, par, pol, seq. Well, function, parametric, we're not going to do parametric equations. Pol is polar coordinates. And if you set that degree mode, set it here, probably best, well, take a look at whether you're using degrees or radians. And then when you hit the y equal key, you'll notice that it's going to say r equals, and then usually you put in a function of theta at that point, which if you're unsure of it, look, there's a little button that says link. It's got an x where you put in an x when you're entering a function. Well, it says x, t, theta, and n. It's kind of a multi-use depending. And when we're in polar coordinates, it's theta is what you're entering. Okay, so I want to show you some stuff just to get you interested here. There's a lot of fun stuff you can do with polar coordinates. This is a program you'll find on Mac. It comes with all Macs. It's called Grapher. I have to wait for it to warm up. All right. So with Grapher, you have a choice. I guess I should go back to the year. you'll get an option here where you can have a regular, this is kind of a cool program you should know about anyway, if you have a Mac or you can borrow one. It'll do 3D graphs, polar graphs, all sorts of stuff. All right, but I have a polar graph up here. And if I just said r equals 4. Wow. Let me use a smaller number. R equals 2. I'm putting in an equation. And you can see it's just drawn a circle here. 2. So that's kind of boring. But you'll find that some interesting things happen when you use trig functions. So I want theta. Okay, that's interesting. R equals cosine of theta. Just a little circle here. Okay, well, that's interesting. Still a little boring. But let me increase the amplitude here, a little bigger. Bigger yet. Now, if I get in here to theta, and I say 2 theta, oh, so then I got a propeller. Oh, what if it's a 3? Okay, so that's some interesting stuff you can do. What would happen if we put in tangents? I don't really know. It's interesting. It looks like a little like a parabola, but not a parabola. There's one more thing I was thinking of. If you say r equals say 0.5 theta. Oh, now we have a spiral. So there's some real cool math, the real interesting figures you can look at. If you're interested, just Google polar coordinates, find like the Wikipedia article, and it'll kind of push you in this direction. Again, this is just cool stuff. We're not gonna put this on the exam. But this is something you can do with polar coordinates. Now there's one thing you want to be aware of with polar coordinates, which is, unlike xy coordinates, they're not unique. For example, if I have this point here, 4 pi over 4, and I have the point 4 pi over 4 plus 2 pi, well, pi over 4 and around, it's the same, I'm going to get the same point. So the coordinates are not unique. Also, if r is 0, it doesn't really matter what the angle is, right? That's the origin. It's always going to be the origin. All right. So we would like to know how to shift between x and y coordinates and polar coordinates. If I give you some x, y coordinates and you want to find the polar coordinates, or vice versa, you want to know how to do that. So again, we'll take a look at this point here, and we'll note that theta r this is the x coordinate, and this is the y coordinate. And you'll note that this x here, well, let me write this the right way. The cosine of theta is equal to x over r. That's just our triangle trigonometry here, right? And likewise, the sine of theta is equal to y over r. But that just means that x is equal to r cosine theta. And y is r sine theta. So we immediately have a way, if we have polar coordinates, to convert them to x and y coordinates. Very easy to just meet our trig functions. Let's do an example. I have the polar coordinate 4, 2 pi over 3. And I want x and y coordinates. So x is 4 cosine of 2 pi over 3. Y is 4 sine of 2 pi over 3. All right, now we have to go back to our trig knowledge and we have to think about what could those be. Well, where is 2/3 pi? The angle 2/3 pi. That's 2/3 of 180, 120. So this angle here is 60. So we have a 30, our familiar 30, 60, 90 triangle. This is 4. What's the cosine of 60? Question? No. Well, it's 1/2 times 4, or 2. And the sine is going to be 4 times square root of 3. Well, it's just square root of 3 over 2. It's 2 times square root of 3 over 2. It's this length times the square root of 3. That's how you get from your short leg to your large leg. Oh, so this is just square root of 3. So my xy coordinates turn out to be what? 2 times square root of 3. Oh, but wait. This is minus, isn't it? Right, because it's in the second quadrant. That was kind of the point of this exercise of checking where the angle is. All right, that's going from polar to Cartesian xy coordinates. Going in the other direction is a little trickier. I'll leave this up. First thing to note is if we have x and y, r is really easy because r squared equals x squared plus y squared. That's just the Pythagorean theorem again. So r is just the square root of x squared plus y squared. That's the easy part. Next thing we can note is that y over x is the tangent of theta. Take a look. Is that right? Yeah. Y over x. Sine over cosine. So the inverse tangent of theta, of x of y over x is equal to theta. So that's my theta. Now, at this point, the complication comes in. If you remember, what the inverse tangent function looks like, it's kind of like this. its range is from negative pi to pi. That just, gives us a point in the first and the fourth quadrant. But the point could be in the second or third quadrant, right? So we have to be a little more careful. When we use this formula, we have to look and see, okay, we're going to get an angle in the first or fourth quadrant. But we have to check our x and y's to see their signs. If they're both negative, it's the third quadrant. If I have to take these down. Dyslexia is kicking in here. So if x is minus and y is positive, this is now the second quadrant, right? If they're both negative, it's the third quadrant, and again, plus and minus, this is now the fourth quadrant. Of course, this is the first quadrant. So you actually have to deal with this. You have to take a look. A note to any computer programmers in the audience. Do you have any left? Almost any computer language is going to have functions, sine of x, cosine of x, arc sine of x, arc cosine of x, tangent of x. They may not have secant and cosecant and cotangent because you can get them with a reciprocal. There is a function arctan of x, just like there is on your calculator, and it will return you a number between negative pi and pi. But most computer languages will also have a function named arctan2. Just another function. You give it an xy coordinate, and it figures this out for it. It figures out what quadrant it's in, and it gives you the proper value. So let's do an example by hand. We have 2, negative 2. These are xy coordinates, and we want our theta. So the first part is pretty easy. 2 squared plus minus 2 squared, square root. So that's 4 plus 4 is 8. Square root is 2 square root 2. Okay. Now we want the arc cosine of y over x. So we want the arctan of negative 1. Well, what's your calculator going to tell you the arctan minus 1 is? Tangent would be positive here, negative here, negative here, and positive here. Well, it's going to tell you it's minus 45 or minus pi over 4. That's what your calculator and your computer is going to return to you. Oh, well, that's going to work here because that's exactly the quadrant we're in. So this just becomes minus pi over 4. If you want, you can rewrite that and add 2 pi to it, and then it just becomes 7 pi over 4. Again, polar coordinates do not have a unique representation. Points on a polar graph don't have a unique set of coordinates. All right, that's all we're gonna do more with polar coordinates, but that's all we're gonna do right now. Again, there's a lot of fun stuff we can learn. But we're learning this today because we're going to apply it in an incredibly beautiful example of math. Let's see. Yeah, I guess we can get started. We should get started. If you haven't seen this before, it's going to be busy when you leave. Well, no guarantees. Okay, so we're going to talk about complex numbers. Remember complex numbers, a plus bi. I is the square root of -1 in polar coordinates. Before we get there, we're gonna do a few definitions here. We're going to start by using the variable z to mean some complex number. You recall, complex numbers have something we call a conjugate. If a plus bi is our complex number, then its conjugate is a minus bi. Conjugate. And you may remember if you multiply a plus bi times a minus bi, you're going to get a squared plus b squared. It's going to be quite convenient. So we're going to give a name to the conjugate. We're going to call it, we have a variable z, which is a plus bi. We're going to have a variable z star, which is a minus bi. And again, as I said, if you multiply z times z star, you're going to get a squared plus b squared. Now, we're going to define a new term here. We're going to say, we're going to reuse something, the absolute value signs, but we're going to call this the modulus of z. And the modulus of z is going to be the square root of z times z conjugate, which in this case is the square root of a squared plus b squared. So if I draw a unit circle, there's a point on it, and we make this the complex plane. The x-axis is the reals, and the y-axis is the imaginary. And we have some point here, a plus bi. Then this distance here, well, I did say it was a unit circle. I guess it's not a unit circle. This distance here, r is just equal to square root of a squared plus b squared, which is our modulus of our imaginary number. A, this is B. So as we did before with our polar coordinates, we're going to rewrite theta. We're going to recognize that A over R is the cosine of theta, and B over R is the sine of theta. Or R equals A cosine theta. I didn't do that, right? A equals R cosine of theta. B equals R sine of theta. This looks an awful lot like our conversion from x and y, except now A is our the real part of our number, and B is the imaginary. So we can rewrite our z now as well. Remember, z is A plus bi, so it's R cosine theta plus I times R sine theta. Or we might want to factor the R. Cosine theta plus I sine theta. Okay. This is what we call the polar form of an imaginary number. It's just the same as if I said A plus bi, except now I'm using polar coordinates on the imaginary plane. All right, so let's see what we can do with this in an example. This is pretty analogous to what we just saw with polar coordinates. Let's say I want z equal 3 plus 4i. I want that in polar form. So first thing I want to do is find out what r is. R is going to be the square root of 3 squared plus 4 squared. That's 9 plus 16 is 25. The square root is 5. Now we have to find theta. Theta, again, is now using our transformation from polar coordinates. It's the arctan of y over x, or 4 over 3. Approximately 0.927 radians. So in the end, we have z is 5 times cosine of 0.927 plus 5 sine of 0.927. And likewise, if I gave you r and theta, you can use this formula to get back to our regular form, our A plus bi form of the complex number. All right, I think we'll let that seep in. If you have some questions, come up and ask me. Let's take a break for a few minutes. Drink. 6, 2, 5, 6, 8, 13. Gosh. I see you're here. Anybody else sneak in? Yes, no. know where we're going, that may help. We're almost there. We'll be there by the end of class. But if I have two complex numbers, like I call W complex number. Previously, we looked at complex numbers and we saw, well, we can add Z and W, we can subtract Z and W, we can multiply Z and W, and we can divide. It's a little different from regular algebra, from regular numbers, but we can do all these functions. Now, what if what we wanted to do was take Z and raise it to the power of W? That's a little weird. I mean, if it was just Z squared, we know what that is. That's just Z times Z, right? We can multiply. This is now to the C plus DI power. What does that even mean? I mean, I know what Z to the C power is, that, just multiplying Z by itself C times, or something like that. But it's raising it to an imaginary power. So that's where we're going. We're going to get there. And that's why we're going through all these hoops to learn polar coordinates and complex numbers in polar coordinates, because that's going to get us there. All right. Go ahead and make room here. So first thing, we're going to take a baby step. We're going to take two numbers Z and W, but instead of using their Cartesian form, we're going to use polar form. So we're going to take two numbers, we're going to call them R1, theta 1, and R2, theta 2. 2 points on a complex plane, but they represent two complex numbers. And we're going to multiply them. That's not what I want to do. Let's just call them Z and W. So, in polar form, we have R1 cosine theta 1 plus I sine theta 1 times R2 cosine theta 2 plus I sine theta 2. All right, what can we do with that? Well, we can bring the R1 and the R2 over here. Now, we have to multiply this expression by this expression, and we're going to use FOIL. So we have cosine theta 1, cosine theta 2. That's the firsts. The outer is cosine theta 1, sine theta 2, plus at the end of class, just a break. Sine theta 1, cosine theta 2, and finally the lasts. I squared sine theta. Did I lift out my eyes? Yes, I lifted out my eyes. I squared sine theta 1, sine theta 2. I squared is, of course, minus 1. So let's again rearrange these. Put together the real part and the imaginary part. So we have cosine theta 1, cosine theta 2, minus sine theta 1 sine theta 2 plus I times sine theta 1 cosine theta 2. Well, I did it backwards, but it doesn't matter. Sine theta 2 cosine theta 1. Okay, now we got to stare at this expression a little bit. Cosine 1, cosine 2, minus sine 1, sine 2. We covered this last week. Anyone recall what that is? It's an important formula. It's the addition formula for cosine. Formula, good to know. This is cosine of theta 1 plus theta 2. What we got here? Sine 1 cosine 2, sine 2 cosine 1. Sine theta 1 plus theta 2. Oh, that's really interesting. Let's just make R1 and R2 for 1 per second. So we just got a unit circle. We've got theta 1, and multiplying R1 theta 1 times R2 theta 2. And what happens on this graph? We're just adding the angles. That's already pretty interesting. When you're dealing with polar form of complex numbers, and you multiply them, all you're doing is adding the angles. That's kind of neat. Similarly, if I were, to divide z by w, I would get R1 over R2 cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. In other words, if we divide, we're just subtracting the angles. We got to try this. We'll try a real example of this. This feels a little like logarithms, doesn't it? Like you multiply two numbers, you just add their logs. Well, okay. Let's make z equal to radius r2 cosine pi over 4 plus I sine pi over 4. It's the polar form. You can figure out what this is. Cosine of pi over 4 is what? Cosine of 45 degrees. Anyone? Know that one? Yes.
No, I am second.
45 degrees, isosceles right triangle, the hypotenuse is 1, what are the sides? Oh, some of you were just too shy to say something. Half the class is missing, it's only half is embarrassing if you're wrong. 1 over the square root of 2. So this number is 2 over the square root of 2 plus 2 over the square root of 2. Okay. That's the AB form. All right, that's Z. W is going to be 5 cosine pi over 3 plus I sine pi over 3. Same question. Cosine of pi over 3, that's 60 degrees. It's going to be 1/2, 5/2 plus I times 5 times the square root of 3 over 2. That's W. So I want to multiply these. So what do? 2 times 5, that's R1 times R2. And cosine of pi over 4 plus pi over 3 plus I sine pi over 4 plus pi over 3. I should figure out what that is. That's 7 pi over 12. You can multiply complex numbers in polar form by just adding their angles. Okay. That brings up another kind of nice possibility. Z squared. Well, just following along here, it's going to be R squared times cosine 2 theta plus I sine 2 theta. For that matter, Z to the n is just R to the n cosine n theta plus I sine n theta. Nice. We can show this by just multiplying two numbers. We can show that it works for n using proof by induction. Recall, useful for showing some truth for any n. We're not going to do that. Do an example. Let Z equals 1/2 plus 1/2 I. We want to find z to the 10th. Now we could do a lot of algebra here, but we can save time. First, and we find the modulus, the r, that's square root of 1/2 squared plus 1/2 squared. That's 1/4 plus 1/4, square root of half. And theta is the arctan of 1/2 over 1/2. This is 1, this is 45 degrees, or pi over 4. So we have that z is 1 over the square root of 2 times the cosine of pi over 4 plus I and the sine of pi over 4. So z to the 10th will be 1 over the square root of 2 to the 10th. That's 1 over 2 to the 5th. 2, 4, 8, 16, 32. No. 1 over 32. Cosine of 10 pi over 4 plus I sine of 10 pi over 4. Well, we can simplify that a little, right? Like 8 pi over 4 is 2 pi. So that's just going around the angle again. So I'm left with 2 pi over 4 or pi over 2. So we end up with just e to the 10th equals 1 over 32 cosine pi over 2 plus I sine pi over 2. Oh, wait a minute. Is the cosine of pi over 2? Cosine of pi over 2.
Is 0.
It's 0. What's the sine of pi over 2?
Is 1.
It's just 1. Okay. A lot less work than trying to do this in Cartesian coordinates. My pages are stuck together. Okay. If z to the n is r to the n cosine of n theta plus I sine of n theta, let me rename this W. Now I want to know what W to the 1 over n is. R to the n times 1 over n. Cosine of n theta over n plus I sine of n theta over n. I did that wrong. Hold on. I get, I'm too jazzed up to do this right. What I want to get to is that r to the All right, z to the 1 over n is just going to be r to the 1 over n cosine theta over n plus I sine theta over n. I guess I could do this just with a substitution, but it's not, I guess it's not so obvious. Okay, so now, before we get to the really fun stuff, there is something practical we can do with this. In higher math, what we often want to do is find something called the roots of unity. That is, if I have an expression, say x to the 5th equals 1, well, how many roots does that have? That's 5. We looked at that, we looked at the fundamental theorem and algebra. We know one of them is 1, but how do we find the other ones? So we're gonna look at a technique that we could use to find the roots of unity. We're gonna do a different problem. We're gonna look at x to the 6th equals minus 1. So if you like, the roots of minus 1. All right, so we need a polar expression for minus 1. So let's see, z equals 1 times cosine of pi plus I sine of pi. But to make things easier, I'm going to write in here plus 2 pi n. Okay, take a look at that, convince yourself that makes sense. Cosine of pi is 0. Wait a minute. Cosine of pi is minus 1. Adding 2 pi n doesn't do anything. Sine of pi is 0. Adding 2 pi n doesn't do anything to it. So this is a form of minus 1. So to find minus 1 to the 1/6, find this 6 roots of it, we use our formula. It's 1 to the 1/6 cosine of pi plus 2 pi n over 6 plus pi sine of pi plus 2 pi n over 6. Now all we have to do is check this for different values of n. So for n equals 0, this is pi over 6. That's 30 degrees. Cosine of 30 degrees is square root of 3 over 2 plus 5 times, again, sine of 30 degrees, 1/2. Okay. Guess I'm going to need this board over here. For n equals 1, that's cosine of 3 pi over 6, which is pi over 2 plus pi sine of pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. It's I. Oh. So I to the 6th is going to equal -1. Okay, so I'll just draw that here. For n equals 2, that's cosine of 5 pi over 6 plus I sine of 5 pi over 6. Okay, we have to think a little. This is like 30 degrees in the second quadrant, right? So that's going to be what? It's going to be, if you believe my notes, negative square root of 3 over 2 plus I over 2. And if we keep going, you know, we're going to get other values. I can just write in minus square root of 3 over 2 minus 1/2 I, negative I, and square root of 3 over 2 minus I over 2. So actually what we have here, you can write this kind of conveniently, plus or minus square root of 3 over 2, plus or minus 2, and plus or minus I. So this is 4 roots, 2 roots, 6 roots. Those are our 6 roots, 6 roots of -1. So any of these numbers, you multiply by themselves 6 times, you're going to get -1. I told you where we're going. We're still not there yet, so maybe take a deep breath. Look now at something called Euler's equation. Euler being, he's kind of like top shelf mathematician. Up there with Newton, Gauss, you name it. He's up on top. Okay, so we want to look at this idea of some number raised to a complex number. We'll call that A plus BI. And we want this to make sense, so we want this to follow the laws of exponents. So that says this has to be A to the A, little a, times A to the BI. And we know what this is. We know what raising A to a real number is, even if A is complex. It's just another number. So this is the part A to the BI that we have to focus on, because it's not really clear what that is. We don't quite have all the math we need to figure this out. We have most of it. But as a consequence, we're going to kind of go about it a little backwards. Let me show you what I mean. We're going to define a function f of theta to be cosine theta plus I sine theta. And of course, as we saw before, f of theta 1 times f of theta 2 will be cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. And, you know, we've done this operation before. This is cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. That just means this becomes f of theta 1 plus theta 2. Now, why did we do that? Well, that's kind of what we want out of this. We want, when you multiply this thing, we can do it just by adding these angles. So if we define a to the bi as f of theta, it's going to work, right? Because we have a to the b 1 theta times a to the b 2 theta. I'm sorry. What I want? That's just going to be, I don't know, I guess I could call it f1 of theta, f2 of theta, which will be, it's not what I want to do. I want to give these numbers 1, 2, 1, 2. That becomes f of theta 1 plus theta 2. So it just becomes a of, I don't know why I'm putting these in there. All right. Okay, that's great. We've got this way of defining things so we can raise something to imaginary power. What we don't know is, what is A? A is some number. And that's the hole in our knowledge here. We don't have the equipment to figure out A. To get that, you're going to need to take calculus. So I'm just going to tell you that A, curiously enough, is our curious number E, approximately 2.71828. E, named after Euler. And thus we get Euler's equation, which is, our A to the I theta is, like this term, f of theta, is e to the I theta, is cosine theta plus I sine theta. This being Euler's equation. That's really hard to fathom. Take this funny, weird number, e, we raise it to an imaginary value, some number times I, and we end up with cosine of that number plus I sine of that number. This is like one of the most, wacky things you'll run into in math at this level. If you want to go on, there's even better stuff, but this is really wild. There's one more piece of this which you may have run into. I know I've run into high school teachers who like to amaze their students, but if you take Euler's equation, e to the I theta, and you substitute pi, you get e to the I pi, cosine pi, plus I sine pi. sine of theta is 0, cosine of theta is -1. So you get e to the I pi equals -1. This is called Euler's identity. -1. And again, it's quite amazing. We've got all these special numbers in mathematics. E, I, theta, -1 all together in a simple equation. Some people like to write it this way. They like to write e to the I theta plus 1 equals 0. That way, we're making one special number and get another special number and there's 0. That's as far as we're going to go with complex numbers. Really kind of I get excited about it. I don't think I'm jumping out of our seat. But any questions? Well, have a nice Thanksgiving. Is there anyone here who was planning or wants to see me in office hours? No? Okay.